We have another example simulation here. This time we've got a number of initial constructs within the test bench. We've 3 different initial constructs, and the design module in this example models a 2-input OR gate. Let's go through the simulation for this example. The processes, reg variables and wires for the simulation are shown in this yellow area. And at the start of the simulation, we have the 3 initial constructs added to the active event queue. The simulator is free to select any one of the 3 initials to begin with. Let's say the simulator picks the first one and begins with the statement in1 equals 0. For this simulation run, we'll combine, update and evaluation events. In1 is x, and after that statement, in1 changes to 0. When in1 changes, this triggers an assign statement, the assign statement a equals in1 to be added to the active event queue. At this point, the simulator can continue with this initial construct, or it could pick any one of the 3 other events in the active event queue. We will continue with this first initial construct. The next statement is #4 in1 equals 1. The #4 is a delay control, causing the statement in1 to be delayed 4 time units from the current time. So this initial construct will be moved to the future event queue for time 4. We now have 3 events in the active event queue. The simulator can pick any one of those 3. Let's just go with the first one here. And the first statement inside that initial is the statement in2 equals 0. That's going to cause an update to in2 from an x to a 0, and that then triggers this assign statement to be added to the active event queue. Moving on to the next statement inside this initial, we've got another delay control #2. So this initial construct will be delayed 2 time units from the current time, meaning it's scheduled for time 2 in the future event queue. We're left with 3 events in the active event queue. Let's go with the initial construct, and the statement in here is a display statement. If we look at the full code, you can see that this display outputs the values in in1, in2 and out1. So in1 is 0, in2 is 0, and out1 has the value x. So when that display occurs, it outputs 0, 0 for in1 and in2 and x for out1. And this occurs at time 0, which is the current time for the simulator. Now we're modeling an OR gate, and we know that if we OR a 0 with a 0, the output is 0, but instead what's output here is the value x, which is incorrect. We'll leave that for the moment, and we move on to the next statement inside the initial. The delay control #2 causes it to be delayed by 2 time units from the current time, moving it into the future event queue for time 2. Now we're left with the 2 events shown here. Either one can be picked. Let's go with the first one. A is updated to in1, so A currently is x, so the update changes the x to a 0, and the change in A triggers this assign statement to be added to the active event queue. 2 events in the active event queue. Picking this one, B is updated, and B changes from an x to a 0. Now you'll note B is on the right hand side here for this assign statement, but because it's already in the active event queue, it's not added a second time. We've only 1 event in the active event queue. When that event is handled, A is ORed with B, we've 0 ORed with 0, giving us 0, and 0 is used to update C. So C changes from an x to a 0. C is on the right hand side of this assign statement, thereby triggering this assign statement to be added to the active event queue. When that event is handled, out1 is updated with the value of C. C is 0, so out1 changes to 0. We've no new events added to the active event queue, and the active event queue is now empty. At this point, looking to the future event queue, the next earliest time is time 2, and there are 2 events at time 2. So those 2 events are brought back into the active event queue, and the time moves forward to the time t is equal to 2. Either one of these events can be selected. Let's go with the first one. And the next statement in this initial construct is in2 is equal to 1. In2 is updated to 1. That triggers this assign to be added. So a new event is added to the active event queue, and we move on to the next statement inside the initial. #6 indicates that we delay 6 time units from our current time, so this initial is moved into the future queue for time 8. 2 events in the active event queue. Let's go with this one. The next statement is the display. When the display is carried out, the value of in1, which is 0, in2, which is 1, and out1, which is 0, are displayed to the output at the current time, which is 2. Here again we have a problem. 0 ORed with 1 is not 0, so the output is incorrect. Continuing, #4 is a delay control. We're currently at time 2, so this initial construct is moved to the time 2 plus 4, which is 6 in the future event queue. One event in the active event queue, let's handle it. B is updated with in2. In2 is 1. B currently is 0, and when we update it, it changes from a 0 to a 1, and it also triggers the addition of this assign to the active event queue. Handling this event, A ORed with B. A is 0, B is 1. The OR operation gives us a result of 1, and 1 is assigned to C. So C changes to 1. That then triggers the addition of this assign statement to the active event queue. Handling that, the output then changes from a 0 to a 1. And now we are left with an empty active event queue. Looking to the future event queue, the next earliest time is the time 4, and there's only one event. Let's move that into the active event queue. The statement to be carried out is in1 is equal to 1. So we change in1 from a 0 to a 1, and that triggers the addition of this assign statement to the active event queue. We're now at the end of this initial construct, nothing more to do, so we can remove that event. One event in the active event queue. Selecting this event, A is updated with in1. In1 has the value 1, so A changes from 0 to 1. And this triggers this assign statement to be added as an event in the active event queue. Evaluating this assign statement, A ORed with B gives us 1 ORed with 1, which is 1. And because C currently has the value 1, this does not trigger any new events. Our event queue is now empty. We look to the future event queue. The next earliest time is time 6, and we have just one event at that time, so that's moved into the active event queue. We continue processing where we left off, which is with this display, and that displays in1, in2, and out1. So we have the values 1, 1, and 1. So finally we get an output which is actually correct. The next statement in this initial is #6 display. We wait 6 time units from where we are currently at. We're currently at time 6. If we wait 6, that puts the initial construct into the future event queue for time 12. Our next earliest time is time 8. Our next statement is in2 is equal to 0. So let's change in2 from 1 to 0. That triggers this assign statement to be added as an event. And at this point, we're finished with this initial. That leaves us with this event. Updating B changes it to 0. And that triggers this assign statement to be added as shown. And when this event is handled, A ORed with B gives us 1. And what you'll note is that C is already 1. So no new events are added. And the active event queue is empty. We've only one event in the future event queue, so let's move that to the active event queue. And the only statement we're left with is this display, which when handled outputs this entry at time 12, which is our current time. And now we're finished. We've no further events to handle. What this example highlights is a problem with the use of the display task, whereby it is completed during the simulation cycle before all signals have been updated. And that's the reason we have incorrect outputs for the first two lines of our output. This is because of the inherent non-determinism that exists due to the arbitrary selection of events from the active event queue. It's possible that the simulator could produce the correct output for the OR gate had the events in the active event queue occurred in a different order. On the face of it, this does not look good, and the question arises, does this mean that sometimes the simulator produces the correct answer and other times the wrong answer? The answer to this question is yes, if we are not careful. And the problem with this example is the way in which the display task is scheduled. Don't try to display signals during a simulation cycle where transitions are taking place. And one solution is to ensure that the display task is in a time slot where no other events occur. An example of that is with this code. You can see that I've modified the delay controls for the display tasks in such a way that the display will never occur during time slots where the signals are changing. And the code shown here will always produce the correct output. This approach is a slightly messy solution to our problem in that we have to take care to ensure that the displayed statements always occur in time slots where signals are not changing. A better solution is to use the strobe task instead of display. Strobe, when scheduled at a given time t, is only executed after the active event queue is empty. That is, after all signals have been updated. Therefore, the output from strobe is not impacted by the non-deterministic selection of events from the active event queue. So all we've done with our code is replace the display task with the strobe task. Everything else remains the same, including the delay controls. It's best to use strobe instead of display when outputting signal values, and in practice there are very few situations in which the display task is required instead of strobe. A third solution is to use another system task that's similar to display and strobe, and this is called the monitor task. It has the advantage that it only needs to be included once in the code, and is normally located at the start of an initial construct. The way in which it works is that it will only print out values if any of its arguments have changed in value from the last simulation cycle. So in our example here, the three arguments are in1, in2, and out1. The way in which it works is that when the simulator encounters the monitor task, it will only output to the display when there is a change on one of the arguments, and any change is only detected at the end of the simulation cycle. A major advantage of using the monitor task is that it only needs to be included once in the code, unlike the strobe and display, which must be coded at any time steps where an output is required. In this example, the output due to monitor looks like this, and you can see the output reflects the correct truth table for an OR gate. To summarize, we covered a simplified simulation model with an active event queue and a future event queue. We explained update and evaluation events and how events are processed during the simulation cycle. In general, you can combine the update event with the evaluation event, as the need for a separate update event is only required for a later topic in the course. The simulation cycle takes place in 0 time from the point of view of simulation time. Due to the unpredictable order of selecting processes in the active event queue, there is potential for non-deterministic simulation results. While this appears unsatisfactory, designers using Verilog for modeling designs follow guidelines to avoid such issues, and it's not a problem in practice. It's best to use monitor or strobe system tasks when displaying output from simulation runs so as to ensure deterministic simulation runs. And to guarantee deterministic operation, you must ensure that a variable is only updated with an assignment in one initial construct.